Hello, I am Salvitius, currently a second year IR student at IT Bombay. This presentation is a part of my Summer of Science project, SOS 2025, where I explored artificial intelligence and machine learning, diving into the foundational concepts and application. Today, I'll be focusing on one such core concept, regularized regression, specifically Ridge and Lasso regression, and how they come to help and solve a major challenge in machine learning. So, as we build machine learning models, particularly regression models, we often encounter a critical issue. The model may perform well on the training data, but poorly on the unseen data. This phenomenon is called as overfitting, and it occurs when a model becomes too complex and starts memorizing the data, including the noise. To prevent this, we use regularization, which modifies the learning process by adding constraints that keep the model simpler and more generalizable. And the model that overfit the exhibition, poor prediction, and unseen data due to the inability to generalize the learned patterns. Let's define the overfitting more precisely. It happens when a model captures both the true pattern and the random noise in the training data. The result? It performs very well on the training set, but fails a test or the real world data. It's like is acing the mock test by memorizing the questions, but failing the actual exam in itself. Overfitting leads to high variance, poor generalization, and ultimately unreliable predictions. And the regularization techniques that we use to accommodate this problem is Ridge and Lasso. It introduces the penalty on the model complexity and it constrains the coefficients, and regularization helps balancing both between the fitting and the training data. And to understand regularization, we need to first revisit the linear regression. In linear regression, we try to learn a functional form y is equals to wx plus b, where w are the weights, b is the bias. We use mean squared error MSE as a loss function, which measures the average square difference between predicted and actual values, where MSE is equals to 1 by n summation of yi minus mean of yi the whole square. And MSE limitations in the noisy environment. Now, here's the problem. MSE works well when the data is clean, but in the real world scenarios, our data sets are often very noisy with redundant and irrelevant features. In such cases, plain linear regression tries to minimize the error by adjusting all the coefficients, even the ones which are having useless features, leading to overfitting. That's why we need a mechanism to penalize the complexity, and this is where Ridge and Lasso come in. Let's start with ridge regression, also known as L2 regularization. It modifies the loss function by adding a penalty term, the sum of the squares of the coefficients, MSE plus lambda summation of W squared. What it basically does is that it shrinks the coefficients and it never sets them to a zero. This is important as it is useful when all the features contribute something, but they want to reduce their impact to avoid the overfitting. It's particularly effective in the presence of a multicollinearity where features are highly correlated. And as to where to use the ridge regression is when you have three conditions. You don't want to eliminate any features but reduce their individual effects. May have many correlated features. You're more concerned about the prediction accuracy than the feature interpretability. Now, let's go to lasso regression, also known as L1 regularization. Instead of the square penalty, lasso as the absolute values of the coefficients. Loss is equals to MSE plus lambda summation of WJ. What it basically does that makes the lasso so powerful is its ability to automatic feature selection by pushing some coefficients exactly to zero. And the lasso effectively removes the irrelevant features from the model. This leads to simpler, more interpretable models, which are crucial working for the high dimensional data when the model explainability is its priority. And now, to understand how the lasso and the ridge behave differently, let's look at its geometry. In ridge, the constraints region are circle, while in lasso, it's a diamond. When the loss function contours touch the constraints, lasso's corners are more likely to hit the axis, which causes the coefficients to become zero. Now, let's try to visualize the constraint shape. As you can see here, the visual comparison. The ridge circular constraint leads to smooth shrinkage. Lasso's diamond constraint leads to sparse solution. This simple geometric difference is what allows Lasso to perform feature elimination, something Ridge cannot do on its own. The ridge circular contour means smooth reduction in the coefficient size, whereas Lasso, the corners, the diamonds represent the potential of the exact zeros. Now, you might be having questions. So, which should you choose? Now, here's the thing. You should choose ridge when you suspect all the features are useful, but are just noisy. And you should choose Lasso when you want a simpler model with a fewer feature. If the data set has more features than samples, then the Lasso shines. But what if you want to have the best of the both? Here's when the elastic net comes in. It combines L1 and L2 penalties. Loss is equals to MSE plus alpha 1 summation of Wj plus alpha 2 summation of Wj square. It often is a go-to in the real world high dimensional problems, and regularization techniques are integral for the improving the model robustness and generalization. Ridge and Lasso serve distinct purposes, with elastic net acting as a versatile option to which enables both the advantages in mitigating the limitations. Now, let's conclude here. Regularization helps us build robust, generalized ML models. Rich helps us keep the features but reduces the complexity. Lasso selects the features by zeroing out the irrelevant ones. Elastic Net gives us flexible balance of both. Understanding these techniques is a crucial for AI/ML practitioner, as they allow us to train better models, especially when the data is imperfect. Thank you for listening.